you yesterday. So I will start with discussing that. I was thinking, some people asked for some extensions, but system is already closed. So I think we are not extending. I would extend the other next assignment by a week. Okay, so let's get started with the problem sheet and then leave it open for discussions afterwards. But before I do that, any questions, comments, anything? Okay.
Sir, will our submission be accepted if we send you by mail on Wednesday?
But the problem is I'm going to discuss the questions now. So I don't know. And then I have to be fair to everyone and make that announcement. So which I have not done. So my suggestion is send it by mail right away, whatever you have. And then, yeah, that's all. That's the best we can do. Yeah, I thought of extending it, but I figured apparently the system is closed and it's hard to do changes. And to be fair to everyone, what I would suggest is anybody wants to submit the assignment, please, I mean, if they still want, send it right away. I will accept it. Mail it to me. Yeah. Okay. And overall, I think there were like 6 assignments. I'm going to pick the best 4 out of the 6 for your final evaluation. And then we will have one final exam after all the assignments are over. Again, it will be a take home kind of a final exam covering all the topics. Okay. So that's the plan. Any questions? Yeah. Okay. So again, I know some of the questions are straightforward for some people, but not for others. So, question 1 asks for BFS runtime. If you use adjacency list or if you use adjacency matrix. In particular, why is it m plus n if you use adjacency matrix? And why is it n square if you use adjacency? Sorry, it's m plus n if you use adjacency list, and it's n square if we use adjacency matrix. So again, the whole point, I mean, since I have a fairly good experience of how you're all teaching, so there are, questions are chosen specifically to strengthen your understanding. So question will help you understand why it is m plus n. And everybody looks at it and says it's BFS is m plus n, adjacency list. Why? And in particular, the way you will understand it better is if suppose it's adjacency matrix and it's more n square. So another question is m is at most n square anyway, right? Can somebody tell me why? M, the number of edges in the graph, in a simple graph, is at most n square, right? Can somebody tell me why it is at most n square?
For dense graph?
In any, I said at most. So in any graph, any simple graph on n vertices, the number of edges can be, what is the maximum number of edges?
NC2.
NC2, right? So it's at most like in the order of n square. So somebody might ask, even m plus n is order n square. So what's the big deal? Why are you even distinguishing this? Okay, can somebody answer that? Before we even
Actually, if we take a complete graph, then whenever we have a complete graph, then we have at most n into n minus 1 upon 2 edges.
correct.
So if
So
we
that's
solve that also, then we will also get n square.
correct. That's the point. So why am I making a big deal about these two different runtime? Because the first runtime is also big of n square anyway, because m is at most n square. So why is this? Why is the difference even important?
Suppose if the given graph is a tree, then it can be done in order of n.
Exactly, right? So the first way of representing the complexity is tighter, little better, because it tells you that if m is small, then the overall complexity is small, and if m is big, the overall complexity is big, up to n square. So there is a parameterization there as a function of m. So in particular, if the graph is very sparse, it's, for example, a tree. Do you know any other graph which has where m is order n? For example, a cubic graph. How many edges are there in a cubic graph?
So 12 edges.
No. There are n vertices. N is the number of vertices, but the graph has maximum degree 3. So what is the maximum number of edges you can have? So by cubic graph, I mean a graph with maximum degree 3 or a degree at most 3. You have a graph where the maximum degree in the graph is, or at
24.
every vertex is degree at most 3. Yeah.
24, sir.
How many?
24.
No, it should be a function of n, right? N
Three
is the number of
Okay.
vertices.
It should be a function of n. Okay.
Because there are n vertices, right?
3n, sir.
Yeah. Actually, not precise. 3n is the total degree possible. So the number of edges will be
3n by 2.
3n by 2. Exactly, right? Remember, sum of the degrees is twice the number of edges. So if you sum the degrees and divide by 2, that is the number of edges. So if the degrees are all at most 3, then there are at most 3n by 2. So that is another class of graphs where m can be order n. In particular, any bounded degree graph. Okay, planar graphs is another class of graphs where the number of edges is order n. So the first runtime complexity can be linear in some classes of graphs, whereas the second one is always saying order n square. So that's why the difference in the complexity measure is important. Okay, good. So because if your input is sparse, then m can be order n and you're done. It's a linear time algorithm. Okay, so now let's get to why is BFS taking m plus n time if you use adjacency list. Can somebody tell me that? And in particular, this requires you to have a reasonably precise description of BFS, right? Because you can't analyze an algorithm unless you have a reasonable description of the algorithm. So what is the complexity of BFS?
There are n vertices.
Okay.
So there will be n cell array, n size array.
Okay. It will be like this. Okay.
And
So what happens in
vertex have some neighbors.
Yes.
So the sum of the edges is 2m, that is approximately m.
Sum of the degrees.
Yeah. So yeah. So 2m, and 2m means asymptotically approximate to m. So m plus n.
Yeah, but you have not described the algorithm for me, right? You can't just simply say, describe the BFS algorithm. We are talking about the complexity of BFS algorithm. So you have to describe it clearly, and then only you can analyze the runtime.
It explores all its neighbors.
Okay. So where do you start? How do you start?
Start from the start vertex or root.
Yeah. So there is one specific vertex given in BFS. Let's call it S. Okay. Then what do we do?
So we explore all its neighbors. So that is the degree of the
Yeah.
vertex.
Okay. And what do you do?
Then
Explore
we keep it all the neighbors into a queue.
in a queue, right? So what do we do? So I have, let's say, I'm going to write it in English, okay? Then not put S in Q, okay? That's step one. S is some start vertex. Then DQS, DQQ, okay? Whatever the first vertex, first element of Q is DQ'd. So let's say while Q is not empty. This is the way you should start thinking, writing about the program. You may have a good description of the algorithm without worrying about syntax, programming language, all that kind of thing. I will take, so let's say S, some V, let's say is the first vertex. Okay. Then what do we do?
NQ all its neighbor.
Add
NQ all
all
its neighbors.
neighbors of V into Q. And that's it. Essentially, we keep repeating this. Okay. So you don't add all neighbors. There is also some coloring you do, remember?
Yes,
Yeah.
gray and white.
Yes. So you have this white, gray, black. So
Yes.
I'm going to add all white neighbors. So there are some initialization about coloring. Every vertex is colored white, and then all white neighbors of V into Q, color them gray, and color V as black. Okay, so essentially, this is what you keep doing in the entire algorithm. Start from source vertex, add all the white neighbors into the queue, color them gray, color V as black, and then go to the queue and take the first vertex and repeat this. That's it. So you have to have a description of BFS. I mean, you can't simply say graph has this summation degrees, M, and all that kind of thing. Then essentially you're saying every graph algorithm will take M plus N time. That's not true, right? So here it is. You have to have this level. I mean, it need not be complete programming level a program, but at least this level of detail, then you can analyze it. So now if you look at it and say how much time it takes, what are you doing? Essentially, you have a vertex coming in and you're looking at all its neighbors. And if you use an adjacency list, how much time does it take to go to all its neighbors?
Maybe a constant time.
Sorry?
No, maybe a constant time if we use adjacency list because, I mean,
You have to look at all its neighbors, remember, right? So adjacency list. So again, now, how does adjacency list look like? So you have, 1, 2, 3, up to n vertex, and each will have all the neighbors in some sort of a linked list. So now, if I want to go to V, I will go whatever V is some number. So I go here, and then I traverse all its neighbors. So how much time will it take?
okay. And
Degree of that
Degree
vertex.
of, yes.
N in the worst case, but more precisely, degree of that vertex.
Yes.
That is the time it takes to visit all its neighbors. It takes degree of that vertex. And then you're coloring it, color V black, all that is fine, no problem, constant time. So then you put them into the queue. Each insertion into the queue is a constant time. You might add some degree of V many vertices. So overall, in that step, it takes degree of V time. And then you're taking the next vertex, next vertex, next vertex. So it's summation degree V, there'll be order M. And every time there is some constant time you're doing, so it's order M plus N. Right? So it's order 1 plus degree of V summation. Summation over all V. So this will be order N plus N. Okay. Why is it? I mean, can you explore same vertex more than once? Because if you do, then your summation V is not correct, because the same V may keep coming. So the summation degree may repeat it 10 times, n times, you never know. So can you explore the same vertex more than once in the algorithm?
No, because we only look for the uncolored vertex.
Okay.
We NQ only the uncolored vertex.
Right. Once you get out of the queue, it becomes black. Remember? That's the reason we color it as black, to indicate that I have explored it. So next time V will not come into the queue at all, because V is black. We bring in only white vertices inside the queue. So a vertex will be visited only once, maybe not even visited at all sometimes. So it's at most once. So it's summation, some constant time plus degree of the vertex. And this, when you sum over all degree, all vertices, it's order N plus M. Okay, so there are all these little details are important. And you have to have a reasonable description of the algorithm before you can even analyze it. Okay, good. So now let's come back. If I
Sir,
use,
I
question.
have a doubt, sir.
Sure.
The one corresponds to the statements that are included in the while loop, no, sir? The constant time.
For example, coloring V as black.
Okay.
That's
So the
that's
initialization, what I have mentioned in the solution is the first part, initialization of vertices with the color, it takes order n.
yes.
And this step, the while loop, that whole while loop runs in order m. So I had written order m plus n.
That's fair enough. Yeah. Sure. That's also fine. But in the while loop, there is a constant time for each vertex you're doing, because
Yes,
of coloring it black, for example.
yes.
Yeah. So now let's come back. Why does this become n square if I use, where am I using the fact that I am using adjacency list? What happens if you use adjacency matrix? Okay.
So there, because it in visiting the vertices, it is take same as that of the list. But in case of a matrix, to explore the neighbor, we have to explore every row.
How much time will it take?
So it will take, sir, n square time, because we have n vertices, and if we
Wait. To explore all the neighbors of one vertex, how much time will it take in an adjacency matrix?
n.
N. Good. Is that clear to everybody? That's the reason, right? I know it's an absolutely simple question, but you all look at it without deeply thinking, deeply understanding it. That's why I'm belaboring it, right? Then adjacent. So if I have one vertex in an adjacency list, I want to look at all its neighbors. It takes degree many times. But if it's an adjacency matrix, then I have V here. Remember, it's a 0, 1 row. And I have to scan the entire row to find the ones, those are my neighbors. So that takes n time. So then it will be summation V 1 plus n, not 1 plus d. So this is going to be order n square. Okay, hopefully you should be crystal clear about this. Okay, analyzing DFS is a lot more involved because of certain recursion inside. You can look at stack implementation and all that. We're not getting there. But so any questions? So adjacency list, adjacency matrix. No, it's not. Often in some complicated algorithms, this will be the first step. It may not be the only step. So it's important you have understanding of this difference. Adjacency list, adjacency matrix, and why we make a big deal about these two different time differences, because M can be N sometimes in a sparse graph, so then you have a linear timer.
So that was a long time doubt I had actually. Why is it expressed in terms of M and N? Now it is very clear, sir. Thanks a lot.
Good. Okay. So for example, in a planar graph, in a bounded degree graph, in a tree, there are huge classes of graphs where the first algorithm is actually linear. The second algorithm is always n square, regardless of the density of the edges in the graph. Okay, good. Okay. The second question talks about Dijkstra's shortest path algorithm. And again, I think that's what it does, right? Yes. And again, I keep emphasizing about proof of correctness of algorithms. And if you go and look at, we didn't do the proof of correctness in the class. You probably will not do it at all in your class, but at least you should read and understand it. And if you go and look at it, there is a place where it uses the fact that edge weights are positive, not negative. The moment you bring in negative edge weights, Dijkstra's algorithm does not give you shortest path. So I asked for an example. Did somebody have an example? I have an example, but I want to see if anybody has one.
Yeah, sir, there is a directed edge from A to B of cost 4.
Okay, A to B.
Cost 4.
Cost 4, okay.
B to C cost -5.
Very nice.
And A to C cost 2.
Great. Okay. And A is the source.
Yes.
Right? Very nice. Okay, good. So how does Dijkstra's algorithm work? I want to start from A. So it will pick A. And B is at the distance 4 from A. And C is at a distance 2 from A. So it will pick the smallest and bring it in. So C will come inside with the distance of 2. And that doesn't change B's distance. It remains 4 because B is adjacent only to A. There's an edge from A, but not from C. So B will remain as it is. And then B will come inside as at a distance of 4. Right? So finally, it will say A is at distance 0, C is at distance 2, and B is at a distance 4, and that's how it will stop. If you go and simulate carefully Dijkstra's algorithm, this is what will happen. But in reality, C's distance is what? Shortest distance is 4 minus 5 minus 1.
Yeah, because I have a choice that directly A or via B.
Exactly.
The minimum of these two is -1.
Exactly. Whereas Dijkstra's algorithm does not give that. Okay. So it's a very simple example. So again, there are lots of learning in the question I want you to understand.
Sir, I have a doubt. Sorry to interrupt. See, while taking example to prove this, I took the example very cautionally so that, it's A to B is 4 and B to C is -5. We are getting -1.
Yeah.
Is it meaningful to have, this kind of graph But
Negative.
because I chose a graph
Hmm.
where I made this value to be a positive value, but still
Okay.
it is smaller than
Yeah,
the
sure. Let's see. Suppose I have the following. If you are unhappy with -1, suppose I would say -3.
yes.
So then A to C, the distance is 1 through B, but direct distance is 2.
Yes.
So, I mean, so overall distance from A to C is still positive, not negative. But still through B is better. I don't know. Did I understand your question? What is your question again?
No. See, when we were having a B to C as -y, we got the distance for A to C as -1.
Correct.
Okay. I mean, is it meaningful to have a distance?
Which is minus negative number.
Yes. Yeah.
Okay. Yeah. So, yes, I mean, there are situations you can model using directed graph. Don't think of it as a distance. Maybe there is some cost function. Maybe, you know, that if you go from B to C, you lose some 3 rupees or something like that. I mean, rather than thinking of it as a distance, you think of it as some cost function. Then there are situations you can model where, so you can ask even, is it meaningful to have an edge with negative distance? Right? Forget about the total path distance to be negative. Even an edge being negative, is it make sense? Sometimes, yes. I think I don't remember whether Carmen discusses this examples, because sometimes you model it. Don't think of it as a distance. Think of it as a cost.
Okay.
Then there are situations. Okay. So back to where I was. I said there are 2-3 reasons for this question. One, coming up with an example is actually a creative work. It's not something describing an algorithm or proving something. You have to think of an example, then you have to have a good understanding of Dijkstra's algorithm and see what it does and where you will fail. Number two, a big learning that Dijkstra's algorithm requires this assumption that edge weights are non-negative. This is very important. Number three, where is it used? If you go to the proof of correctness of Dijkstra's algorithm, you will see that it is used. So I have emphasized the importance of proof of correctness several times during my lecture, and here is the reason. Because there is no reason otherwise. You can imagine that, oh, the way I am doing some sort of a greedy approach, why should I give you shortest path? And it does. And there is a proof. There is a one-page proof in Carmen's book, you can see. And there you will see that there is a place where they use the fact that distances are non-negative. And in particular, here is an example. If the distance is negative, then it does not give you shortest path. So it just illustrates a number of things. That's the point of this exercise. Okay.
So just to continue with the discussion as the negative edge weight. So that is why I think the Corman book has the Bellman-Ford algorithm, that how to handle this negative
Exactly.
edge weight.
Bellman-Ford, Floyd,
Yeah, Floyd also work for
Floyd,
negative weight.
Warshall, these algorithms can handle negative edge weights.
And it never told about distance, it told edge weights.
Yeah. So I'm not sure everybody followed this example and simulation of Dijkstra's algorithm. Take this example, go run Dijkstra's algorithm and see what it will do. It will tell you that the shortest path from A to C is 2, whereas in reality it is 1 through B. So, but go convince yourself that actually it will say shortest path distance is A to C is 2. And these are, simple enough examples. You can ask even in a problem sheet in assignment for students to try. And what better way to understand Dijkstra's algorithm and proof of correctness than something like very simple stuff. Yeah. Okay, good. So let me get on to the next question. I wanted an implementation of Dijkstra's algorithm, in particular the complexity analysis. Here again, you can do any complexity analysis only if the algorithm description is fairly clear. Okay? So you have to have a clear description of the algorithm. So a high level description is not enough. You have to reasonably closer to a program description, then you can analyze it. Okay. So just like BFS, where you keep on taking the first element and adding all its neighbors into the queue, you do something very similar here, except there are edge weights. So you're paying attention to the edge weight. So how does Dijkstra's algorithm work? So let's say put S in some set S. Okay, initialize distance V is in V minus S. And this is going to be distance from S to V. Or rather, weight of the edge S comma V. Okay, so pictorially, I have set S here. And then for every vertex outside, I initialize a distance. And then let X has the minimum distance. So what he will do, add V to S. Update D of X for all X in neighborhood of V minus S. Okay, I'll write down and then we'll give you a description, the picture, and then we'll do the analysis. But how do I update it? It's going to be minimum of whatever is current distance and then I repeat. Until V minus S is empty. Okay, this is how the algorithm is. So it's sort of like the Q BFS. What we are doing is we compute the distance of every vertex outside, take the smallest vertex and add it to S. So the picture will have your S and then V will come inside. Or rather X really. Now what happens is there are some D distances. Look at only X's neighbors and update their D values. And then repeat. Find the smallest among them, add it to S, and so on. Okay, so is the algorithm clear? I mean, does it look like what exactly Dijkstra does? Because we remember the distance of every vertex through vertices and capitals. And then I delete the smallest among them, add it to capital S. Now, because of this addition, some of the distances may have changed now. Why do they change? Because this new vertex has come into S. Through that vertex, there may be, I get a shorter distance. So I update it to whatever its current distance is, or because B is neighbor, I look at distance of whatever B plus the edge Vx. Whichever is smaller, I update it. And then I continue. Find the smallest out of the D, add it to capital S, keep going. Okay, any questions? Does it look like what Dijkstra? I mean, you should go check it out in a graph and so on. Okay, so always, I mean, this has a very similar flavor as Prim's minimum tree algorithm. So I have this capital S, some vertices, and things outside. Through vertices of capital S, I look at their distances, and then I pick the smallest, add it to the vertex. Because of that vertex getting into S, its neighbors alone may need to be updated. I update them if necessary and keep doing it. Okay, so that's how. Okay, so what is the complexity of this algorithm? I don't know how many of you are even bothered to do the complexity of this in the course. Actually, you should. Okay, so can somebody take a crack at what the complexity would be?
Yeah, so the naive implementation order n square and using binary heap and Fibonacci heap. So
okay, we'll come to that. Why is n square naive implementation?
Yeah, so in naive implementation, I have to find the minimum element every time.
Correct.
So I have to do a linear scan. So find the nearest closest unvisited vertex it takes in every row it takes order n time. And
Correct.
here I also represent the matrix as a weighted adjacency matrix. So to repeat this process for each vertex, it is n square, order n square.
You don't need adjacency matrix list is not an issue here, because this list there are n of them. This is the distance of every vertex outside you have calculated. So there are n of them. You are finding the min among them, and you are deleting it, putting it in capital S, and do some updation of its neighbors. Okay, so all of this is order n for every vertex. Now together it's n square. Okay, n square plus m whatever. Okay, is everybody clear about why this is n square? If you just, I mean, as I said, if you have to analyze the algorithm, make sure you have a complete, clean description of the algorithm. Then only you can analyze it. So here's an description.
So you are saying that whether I use a matrix or
It doesn't matter really, actually. Here it doesn't matter.
Okay.
Yeah. That's not the costly thing here. Here it's the computing these distances. No, actually, no, it does. I mean, in this algorithm, it does not matter. But when you use a heap, it does matter. We'll see why. Okay? So, again, I want you to look at this is the essential description of the algorithm. Whatever I have it in the pink. Okay? So Debajyoti now suggests, okay, let's use a binary heap. Okay, first of all, even if you go there, what is the motivation for binary heap?
Because the some operations are better, efficient. So there are
what
mainly
operations are we doing?
Yeah, mainly three operations we do with binary heap. So insert in
in this algorithm,
extract mean and decrease key.
No, in this algorithm, what are the operations you are doing?
Yeah, in insert, extract mean and decrease key.
I don't see where you're doing insert.
Initially, we insert all the elements into the queue, priority queue.
Yeah, you can do that, but you can think of it as a building a heap also. That's fine. Okay, so that's
So apart from that, we have extract mean and decrease key operation.
exactly. So we are deleting min all the time. So from this list, I am deleting the smallest element, all the time. So delete min is one operation. Then once I delete min, the neighbors of this vertex, which I added, I need to update it in this fashion. Current neighbor plus this distance, whichever is smaller. Okay, so each one is a constant time operation, but how many I'm doing is the neighbors of that vertex. By the way, so this is where adjacency list is important. If I have an adjacency list, I know all its neighbors. It's a weighted adjacency list. I know its neighbors. I know their current distances and compare it with the new distance and see whichever is smaller, I update it. So what I have is required operations on the list is delete min or extract min and change or decrease value. Right? Why? Because I have these D values, I have my set S, and I add my what did I do? That the moment I add a new vertex from here, I look at its neighbors, look at their D values and see, can I change it? Because I added this new vertex, will it decrease? So I update these guys. So that means I need a data structure where I can maintain a set of numbers and support these two operations, delete the smallest element and change some element, decrease certain value. And now it turns out a binary heap supports these two operations in order log n time. Okay, so you go back and maintain your list in a binary heap. Every time you do delete min, it's log n time. Every time you need to do change or decrease the value, it's log n time. So how many number of delete mins and number of decrease keys, the maximum, how many will you do?
N minus 1.
How many times you do delete mins? It's n minus 1. And decrease key? Delete min is 1. Once every time in the loop. How many times you do decrease key? Look at it.
M times M.
Yes, because summation degree. Once you include a vertex, you look at its neighbors. So it's degree. Degree many times, summation degree, so that's order n. So if I use binary heap, I can support these two operations in log n time. So it becomes m plus n log n versus earlier it was just n squared. Okay. So when is this better algorithm? If in particular the graph is sparse, this is a better algorithm if m is n. But if the graph is dense, this is not necessarily a better algorithm because it's an n-square log n algorithm. That's why there are better data structures called Fibonacci heap or some versions of it, where you can perform a sequence of decrease keys in amortized constant time. So there is no m log n, but so this is binary heap using Fibonacci heap. The decrease key takes only constant time amortized, and delete mill takes log n time. So it's m plus n log. Okay, so again, I know we have not done Fibonacci heap. You may not need to, don't bother about it. There is something called Fibonacci heap, which can do decrease key in constant time, not worst case, but amortized time. We didn't get into anything about amortization. But the point of this question is, again, to make sure you are able to analyze the extra shortest path algorithm, which means you need to write down clearly the steps, see what happens in naive implementation. Then if you use a binary heap, first you figure out what data structure is appropriate here. Because you are talking about delete min, binary heap is a natural choice. If you do that, it takes m plus n log n, but there are better structures which can improve it to m plus n log. Okay, any questions?
Sir, do delete min take log n time because we are forming a min heap. Okay, so every time the minimum element will be at the root.
Yes.
Okay, so
Yep.
at the very first, iteration itself, we'll be able to find the minimum element, that is the shortest path or something. So does it take log n? Decrease key is fine, it will take log n. Even heapify, it will take log n. But what about delete min?
So you're saying that min is at the root, so why is it not a constant time, right?
Yes,
Why is it
yes.
log n time? The point is finding min is constant time, but deleting min, you also have to redo, right? The heapify you have to do. So when I say delete min, it should delete min and rebuild the heap. The whole thing takes log n time. It's not about just finding the min. To make readjust the heap, it takes log n time. So delete min, when I say log n times, it means it deletes the min and recreates a new clean heap. All that takes log n time. Remember the swap operation, you delete it, take the last element, put it there, do all the adjustments, bring it back. All that takes log n time.
Okay, okay.
Okay. Next question talks about Kruskal's minimum spanning tree algorithm with and without using disjoint set union find data structure. So again, very similar. Anybody wants to tell me the steps in Kruskal's algorithm?
Short the edges in
Yeah.
increasing order.
Short edges. Yeah, in increasing order. And then let's say now you have
We
yeah,
add
E2,
edges.
edges. Now I have my minimum spanning forest, which let's say starts with E1.
And then we add edges according to the increasing order if it does not form a cycle.
Exactly. If EI does not form a cycle with in F, then F is F union EI. That's all the Kruskal's minimums. So again, step one, if I want to analyze an algorithm, write it down precisely. That's what we've done now. Now I need to analyze it.
Sorting m number of edges, it takes m log m,
Correct.
and this for loop takes order m time. So it is overall.
Wait. Why is it for loop order m time? It's executed m times, but how much time in each loop?
We need to check for a cycle whether there exists
Exactly.
a cycle
I
or
have
not.
a bunch of edges and I'm adding EI. I need to know whether it forms a cycle with that. So you have a graph on some, let's say, I edges. You want to check, does it have a cycle? I mean, one way is to see, you look at the endpoints of EI and see whether there is already a path between these 2 points in F, right? So again, you can analyze it only if you have some description of the algorithm. So if EI equal to U comma V, then this step is check if there is a UV path in F. If there is a UV path in F, then don't add it, otherwise add it. We know how to find whether there is a path between a pair of vertices. How do you check? In any graph, I give you 2 vertices and I want to know, is there a path between those 2 vertices? How do you do?
BFS.
Exactly. Start from one of them, run a BFS and see whether you hit that vertex. So how much time will it take? We know all that m plus n, blah, 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 right? So if, in this case, there are I edges at any point of time, so it will take order I time. So, and if you go all the way, so that's going to be something like 1 plus 2 plus 3 up to m. So it could be as bad as m square. Right? Because all you have to check is whether there is you at any point of time you have a bunch of edges in F. Look at that graph and see whether there is a path from U to B in that path. U and B are in the same connected component. So that we know takes order m plus n or b plus e. Whereas in this case, I may have some I edges at any point of time. At the ith step, I might have included all of them. So it's going to take you some order I time, and you run it over all possible values of I from 2 to m. So that's summation I 2 to m. So that's m square. And this is what we improve it heavily by using this disjoint set union data structure. You first abstract out what is the operation we are trying to do. Given a pair of elements, I want to know whether they are in the same component or different component in the existing graph. So this is exactly disjoint set union. If they are in same component, I am not going to add that edge. If they are in different component, I will add that edge and do a union of the components. They become single component. So this is the set union disjoint data structure. Now you use the data structures, complexity, whatever they use. I think you can do it in m log n. Actually, m log m for the first step. Second step, you will do only n unions. So I think it's something like n log n. You have to go, I don't want to get into the...
Sir,
Yeah.
There is, that union by rank and path.
Yeah, there are all these
heuristics, and there is a concept of inverse Ackermann function.
Yes.
Alpha n. So it is m into alpha n.
Yes. I don't want to even worry about all this sophisticated, heavily complicated path compression analysis and all that. Even if you understand this, I'm happy with it. Okay, so let's go back in both these Dijkstra's algorithm as well as Kruskal's. First step is write down the steps precisely. Then analyze each of the steps in a naive way. And now you identify the required operations, right? So it says, then figure out what data structure is appropriate, use that data structure, use the complexity of the operations in that data structure and get the overall analysis. That's exactly what we are doing in Kruskal's algorithm. Write down the steps, naive implementation, understand what data structures you want. So we want operations are same set. Your collection of sets, you want to maintain it. Given a pair of elements, I want to know whether they are in the same set, and then I want to do a union. If they are in different sets, I want to do this union. These are the operations. So now you go abstract out your operation data structure problem, which we have already looked at. You apply it. So the interesting thing again, people say algorithms plus data structures is programs. Right? Kruskal's algorithms, Prim's algorithms like 1950s, so it's about 70 plus years old. But some of the data structures are only about 30, 40 years old. Same algorithm, you not change the algorithm. Why are the algorithms correct? Well, you need a proof of correctness. That's all done, 1950s. But good data structures give you better implementation of the algorithm. That's all. Questions?
There is a last question.
Yeah, one more question, I'll finish. That's a fairly easy question. I'll finish in 5 minutes. So the last question says, I want to find all cut vertices. Now, I am only asking for a simple, not so efficient algorithm. Okay, I'm asking n into m plus n. So what is a cut vertex? A cut vertex, for example, is something like this. In a graph, so there are 5 vertices in the graph. What are the cut vertices here?
3. It will disconnect the graph.
Only cut vertex. If you delete 3, the graph breaks it into multiple components. 1 is not a cut vertex, 2 is not a cut vertex, any other vertex is not a cut vertex. Okay. I can talk about and if you look at this will be a cut vertex, because if you remove this, there is graph breaks. This will be a cut vertex and so on. So your job is to find all cut vertices in the graph. And I'm giving you a time which is n times m plus n. So how do you define that?
So using DFS, we can find cut vertices in order of n plus m time. So to find all the cut vertices, it will take n into m plus n.
Sorry, using BFS, you will find
DFS, depth first.
You will find what?
One cut vertex.
How?
Because it gets disconnected.
So how will exactly
Connected components,
no, exactly what will you do?
it will find the connected components
Of what? Which graph?
of the given graph.
You'll find the connected components of the given graph. Okay. Let's assume the graph is connected. Maybe I didn't say it clearly, but let's assume. So there is only one connected component.
Choose an arbitrary vertex, delete it, run the DFS on the remaining graph.
Delete it. That's the point. Take for every vertex, delete it. Because that's the definition of a cut vertex. What is the definition of a cut vertex? If you delete it, it breaks it into components. Okay, I should have made it clear. I'm starting with connected graph. So I choose a vertex, delete it, and then run DFS on the remaining graph, G minus V. If it remains connected, then my V is not cut vertex. If it breaks it up, it is a cut vertex. So that's it. So the algorithm would be for I going from 1 to n, run DFS on G minus I if G minus I is disconnected, output I as a cut vertex. That's it. And how much time will it take?
Order of n into n plus m.
Why?
Because the for loop runs for every vertex, so n times. The BFS runs for n plus m, hence n into n plus m.
Exactly. So there is a clever DFS based algorithm which can improve it to n plus n. This is some Tarjan's algorithm. In fact, this is part of Tarjan's PhD thesis, which won him the Turing Award, by the way. But I'm not asking that algorithm. That's involved. Anybody is interested can go look it up. But he manages to find the all cut vertices by just running one DFS. Using some other nice properties and some bookkeeping, he manages to do one DFS, all cut vertices. But my question is to make sure you understand the definition. Again, the point of this question is cut vertex is a new concept I'm introducing in the question. It is not in my videos and not in my lectures. So first, are you able to understand the new concept? That is the first test. All it says is delete it, the remaining graphics should be connected. That's all it says. So that's cut vertex. And can you simply apply some brute force method to find all cut vertices? That's the second point of the exercise. So that's it. Okay, good. It's 9:37. I'm going to stop. Based on some requests, I've postponed the next assignment deadline by a week. So we can discuss next week for any random questions you have on NP completeness or graphs or whatever else we have.
Sir, I have some doubt or discussions on this topic, this graph algorithm. So today, I think it is not good time. It may take around 30 minutes.
Yeah, let's do it next week. Because I have one more week to discuss the problem sheet because I postponed the next problem sheet deadline by a week. So shall we discuss next Monday?
Not any date this week.
I'm not sure. I'm busy this week actually with some various programs. You can send me email. I'll see if there is something quick I can answer it.
Better to discuss. Maybe those are not good for mail.
Okay, so then let's wait till next Monday then.
Okay.
Yeah. Okay, thank you then. Good night.
Thank you,
Bye.
sir.
Thank you, sir.
Thank you, sir.
Yeah, bye.